And I'm also opening the two papers from the paper together for this one, and also I will put them in using your workshop.
Yeah.
Yeah. Good that you would do
Yeah.
Yeah.
Well, the last
Oh,
Second, shirts. Very good. Can people hear us? Good. Okay.
cool. So we get started?
Yeah.
Oh, sure. Yeah, so hi everyone. I'm going to present this paper called Emergent Spatial Temporal Scene Decomposition while Self-Supervision. And this is a paper for this year ICLR submissions. And yeah, so basically it's trying to decompose the driving scenes without any labels. So there are scenes emergent, and also decompose the scenes into four, not just the 3D, but also the temporal consistent way. So basically the input is RGB videos from multiple cameras, and also the LiDAR point cloud information, and they can decompose the RGB information. And here you can see it's not only can reconstruct RGB, it also can decompose into the static and the dynamic fields. And in this figure, you can see it's only contain the static actors, and it remove the dynamic actor front end of vehicles and pedestrians shown in the second figure, second image. And then they can also get in the depth, and also why these two images are the same. Oh, there are two different things. Okay, sounds great. And they can also get in the dynamic depth, and also they can get in the scene flows. So basically, getting where each particle in the 3D is, how each point moves in the 3D space. And also they have some headers, basically lifting the features from the 2D models to the 4D temporal consistent way. So as you can see, this image is basically getting some potential encoding free features from the 2D models. And you can see it's kind of having some semantic information. And in their experiments, they show using those features can be beneficial for the downstream from the perception tasks. Yeah, so I think in their website, they have more demos here. Yeah, you can see given videos, it can first it can reconstruct. The quality is okay. It's not that bad. Yeah, actually, it's quite good. The performance you can see. Apart from there are still some blurry on those dynamic actors. Yeah, but in general, it's high quality, and also it can decompose. You can get in those dynamic actors decomposed without any labels. And yeah, and they can handle different things, static things, dynamic things, and also different conditions, sometimes the night during the nighttime. Cool. And yeah, this is basically what they did in this paper. So before we dive into the details about this paper, so we need to understand some. So this is not the first paper that doing the same task. So previously there is a papers in the 2022 nerves. They called the D2 nerve. This nerve is also this paper. They call the self-supervised decoupling the dynamic and static object from the molecular video. So they are doing the same task actually, but they didn't consider the driving things. So yeah, so basically given videos, they are trying to decompose into the static things and the dynamic things. So as you can see here, there are some scene decomposition. So they are using the nerve, pretty straightforward. So given the position XYZ, given the ray direction, you sample the point along the ray, and then you have a function to map it to the, you have the feature grid here. The notation between the two papers are different, but they kind of similar. Yeah, so given the X, you will get in the features. For you getting the geometry features, which you can get in the, here, this is the density for this point, and also you can get in the color. And here the S means it's static. And you're also having a dynamic field, which here the tau, you can think this as the T, just a encoded version about the time. And so for the time varying part, you just given the X and the view direction, you're getting the density for the dynamic field and also the color for the dynamic field. And how to calculate the color is also because currently for each point you're having the two properties. One is the static properties, another is the dynamic properties. You need to combine these two properties together. So you will basically weighted the color based on its density. So this is how they get in the color for each point. And similarly, you can get in the accumulated transmittance. Yeah, it's just for each point you have two density, and you sum these two density, you get in the final density. And so this is basically the same decompositions, and adding all those stuff, you get in the final RGBs. And they also and so here I didn't mention one thing is called shadow. So shadow is important for the decomposition because it's not a part of static. When the dynamic object moves, the shadow will also move. So the shadow is kind of affected by the dynamic actors. But if we do not do anything, we just do the static and dynamic, basically the network will naturally learn a mean of the shadows. I think, do we have an example? Yeah, maybe in the paper they have an example. Yeah, you can see, oh, I copied that example. Yeah, you can see this image. If there are no not handling the shadow, it's basically just having an average shadow. So when so in this thing, the hand are moving. So you will see the average of the shadow is baked into the static things, and so also need to handle this separately. But those kind of shadow is casted by the dynamic actor. It cannot be just handled by the dynamic fields because those it's not moving. It's just attached to the static objects, but it's casted by the dynamic actors. So what they do is they propose another MLP. This one F row, and it takes the X and also the time, and it's getting the values for each point, and this trying to modulate the static fields. So given the features from the dynamic things, you have another headers that predict the values for each point. For each X, you have this row, and then you will combine this. So you will modulate this, multiply this coefficient with the color about the static, and you sum it with the dynamic color. So this is how they decompose. Yeah, I think it's here. So you can see, compared to the previous one, here there is an additional term added by 1 minus rho, which takes the features and also the time. Yeah, it's basically changing the color for the static things, but it will take the features from the dynamic things. Yeah, cool. And so basically, after there are three fields: the dynamic fields, shadow fields, and the static fields. They're using this function to doing the volume rendering, and then they're getting the final color. But only doing this is not sufficient. There should be some regularization to help you understand, because naturally it can be decomposed to any part, and anything can be the dynamic field. Why it will be decomposed with static things. So there are some regularization. So basically, the first one is they have this weight. This weight is basically the ratio of the dynamic densities versus the total densities. So for each point, we have a weight, and this weight basically means measures how much dynamic about this point X, and we want to basically explain everything in the static field, and we only explain those as necessary for those really dynamic things we want to explain with the dynamic field. But all the other parts, static things, we want to explain with the static field. So they have a function here. Basically, they will calculate this weight is belong to 0 to 1. They want to encourage this to be a binary. It's either to 0 and or 1, and they are using an entropy loss. So encouraging it to be high entropy. So you can see the entropy, they are minimizing the minus entropy. So enlarging the entropy about this weight. And they also mentioned that I think in this paper, in this figure, you can see if the original, this is the entropy loss. Yeah, if you are not doing anything, it will basically, the gradient will be zeros when it's 0.5. So it's hard to optimize during the training. So they have modified this entropy loss with some weights. So it's easier to learn on when it's 0.5 at the initial point. Yeah, so basically there are some different regularizations, and also they have another regularization to, this is the weight. They are trying to minimize the maximum weight. So not explain the things. They try to encourage explaining the things with the static fields, except that it has to be explained by the dynamic. So this is trying to minimize the weight. Yeah, basically, this is the Pierce work. They are trying to doing decompositions with the nerve. They have the two fields: static field, dynamic field. Dynamic field takes the time as the input, and they also have a shadows that basically takes the features from the dynamic fields and then modulate, constrain the color about the static things. So this is how they're getting the final RGB, and they have some regularization to making sure everything, a majority of the thing is explained by the dynamic model, and only those dynamic objects are explained by the dynamic fields. Cool. Yeah, this is basically the prior work. So this work, they are doing quite similar things. So instead of using the nerve, traditional nerve, they are using the hashing grid inside GP. So given the X and given the XT, you will get in the hash features, and then you will have a lightweight MLP to get in the, here G is the features for static features, and Y is this is the density and the dynamic features and the density for the dynamic. And then they have different headers. So given the static features and the view direction, they will get in the static colors. And they have another MLP called color sky. They have a sky model for the background. Yeah, this is widely used in previous work in the urban thing. For instance, the Unisame or StreetServe. They're also having the sky model. So for the sky models, only the view direction is taken as the input, and the MLP, they will get in the sky color. And for the dynamic ones, the same. It will take the dynamic features and the view direction. But the dynamic features is also take the time as the input to get in the dynamic features. And for the shadows, they're taking into the dynamic features, and they have MLP to get in this coefficient role. And how they composing the colors is they using this the average. This is the weight for the static. This is the dynamic, and the static is also times 1 minus rho, which is output by the shadow MLP. And yeah, basically that's everything. And also because they have in the sky models, so you sample K points along the ray for the scene, and then you calculated the accumulated transmittance, and then you times you 1 minus the accumulated transmittance, and then you times the sky color. Yeah, this is how they decompose the scene. Yeah, and similarly as before, they have another loss called the expectations. They minimize the expectation about the density of the dynamic density. So this is the similar as before. They are trying to, because everything can be explained by the dynamic field. So this is the regularization to minimize, to making sure that it's only explained by the dynamic field necessarily at some necessary conditions, only if it's a dynamic actor, hopefully. Yeah. So this is basically the basic version about their approach. And they adapted the D2 nerve to the urban scene situation. And apart from that, they propose another using the flow estimation, because it's naturally that each particle you can imagine in the 3D, each point in the 3D is involved. You can find the dynamic actors, the point will move based on their motions. So they adding another flow field compared to the existing work. So basically the flow field is pretty simple. It's just an MLP header. It takes there also a feature grid for that. So this HV is the feature grid for the flow field. And so given the X and the time T, you will get in the features from the hash grid first. And then you have a MLP headers, MLP V here to get in the velocities for each point X. And given this velocity, you can basically map it to the previous next step and the previous step. You will get in the X prime based on this is the next step, and this is based on the T and the time. So basically they will using this MLP to predict the flow for each point, and then for the dynamic fields, they predict the forward, they do a forward path, they do a forward flow and backward flow, which is VF and VB here. And so given the translated point, the X plus VB, you will get in the position about this point as the last time step, and you get in the feature. And you pass to the dynamic MLP, you are getting the features for this point at the last time step. And you are getting the features at this time step, and you are getting the features at next time step. Yeah, so basically they have they're using 3 frames to get in the feature for the dynamic field, and sum it using a weighted sum and focus on more on the current time step, and they get in the new features, dynamic features. And so basically, yeah, instead of using this directly getting from the X and T, they get in the features. They are using the flow field to get in the 3 features and sum it and pass to the MLP. Yeah, that's the difference about adding the flow estimation or not adding. Cool. And so any questions so far? Yeah, I think that's primarily the everything in this paper. Yeah, it's extending the existing work to the large urban scene settings, which haven't, nobody have tried this before, the self-supervised decomposition on the driving scenes. And it's using the hashing grid instead of just the traditional nerve. And also is having the shadow MLP, the color MLP, and the sky MLP. And they have proposed a new flow estimation module that can getting better feature for the dynamic field, because it will encourage the self-consistencies between the nearby frames. And cool. Yeah, that's basically this paper, Emergent. Yeah, sorry.
We analytically derive the flow field from the dynamic field instead of using another emergent.
Well, what do you mean? Yeah, the question is, can we derive the flow field from the dynamic field analytically.
Right.
Yeah, so what do you mean derive?
I
So
mean, I think dynamic field
Mhm.
already contains the flow information.
Yeah.
My hypothesis. Can we get to the flow information from the dynamic field
Mhm.
instead of using another ML field?
Mhm.
That's my. I'm not sure whether that is the answer.
Yeah, I see. I think, yeah, yeah, that's a good question. I think the dynamic field, you already know the actor position at the previous time and the current time. It's just not explicitly. It's just it will basically given the position x and given the t, and you will directly get in the features.
Right.
And it do not explicitly tell you this point is actually what's the position about this point at the previous time or the future time. So maybe some.
It's kind of an inverse that you want, and you cannot get that from a neural network. So if, for example, if you want to find the correspondence between the same, if you want to find the correspondence between 2 points in 2 time steps, then you need to pass in the other direction. So you say for t and t minus 1, I want this feature, which x would it be? So it's like kind of the inverse. So maybe with a different architecture for dynamic flows, but for like MLPs, I don't think that's straightforward.
Yeah, I think it's so if you do not do nothing, then there is no constraint that there is no explicit constraint on the active on the flow. You don't have the flow. So in my understanding, this flow field is kind of a more explicit priors that human add. So it's basically it need to follow the physics rule. So given the velocity, given the position, you know the point needs to transform in this way. So this is a kind of regularization explicitly. Yeah, if you only have in the dynamic field, maybe it's hard to it do not have such regularization. Yeah, maybe the decomposition will be worse. Yeah, that's my understanding. But yeah, but I guess it's possible if there are some regularization on the dynamic field. We can also add in some self-consistency for the dynamic fields, I guess, similar to doing the flow explicitly. And maybe that will also help. Yeah. Cool. Yeah. So yeah, and another thing in this paper they mentioned is they can also lift in the features from 2D to 4D. So they have the features predicted by the Dino V2 or some vision models or self-supervised features. And then they, given the feature, they can lift it to the 4D. It's pretty straightforward. It's just adding a new MLP header. So given the feature about static field or dynamic fields, you can get in the features. Yeah, you can get in the features. You can having an MLP feature to get in the here F, and then you sum it. You aggregate it based on using the one rendering. You have the sky feature. You have the features for the dynamic things and the static thing, and you sum it all. And then this F hat, capital F hat, is supervised by the features that you predicted by the 2D models. Yeah, so this is a quite a popular approach, or it's already applied in many applications for doing this. For instance, you can not only transfer the features from 2D to 4D, you can also transform the labels from 2D to 4D. Yeah, for instance, there are some work called they are transferring the 2D bounding box into the 4D, like the Panamic PNF, Panamic neural field, I guess, panoptic neural field. Yeah, so given a 2D semantic segmentations, you can also transfer, doing a similar thing. You have MLP header, you are mapping the feature into the 3D. And then, so in that way, you can get in the 3D semantic segmentations. And also similarly, if you have a 2D bounding box, you can do similar things. You can get in a bounding box in the 3D. Yeah, so those are just making the labels or features to be more consistent from multiple views. Instead of just here you get one image, you're getting one model, you predict that. There is no temporary consistency guarantee. But if you do it with the nerf, you can have the consistent guarantees for multiple frames. And they also observe another effect is in their models, they find their predicted features are having this positional encoding patterns. Yeah, you can see here, this is the ground truth and also their predictions. So they want to decompose that. So instead of directly using this function, they model the positional encodings with another MLP. So given the UV position about this image, you're first doing the kind of positional encoding operation and having an MLP, and then you predict this is they call it positional encoding feature, and then by doing this three parts, this feature is learned will be no potential encoding. And they show that by doing so, this feature is more useful to the downstream.
Is this data loss something like a perceptual loss?
Mhm.
So they predict the dialogue features using the ground truth dialogue features as supervision.
Yeah, so in my understanding, I don't think this improves the decomposition. It will give you a header. Basically, will help you getting more consistent features. It's a kind of a refined dino features. So previously it's predicting on only one frame, but currently because you know the geometry, you can apply those features to your 3D space, and then you can get a more consistent prediction. So during the inference, you can just use this you're doing the one rendering, you can getting a revised features for the demo, and it will be more consistent. But it won't because the supervision is in 2D, so it won't give the benefits about decomposition. Yeah, so similarly, we can do we can do semantic segmentation. Given this ones, we can get in the semantic features. We can using MLP to predict that. Then we can get a more consistent prediction about the semantic labels. And yeah, for instance, we also try previously on the 3D. If we have the 3D point clouds, we have the labels, the semantic labels. We can do a similar thing. We can learn a header and render it on the 2D. So in this case, you are bringing those label information from sparse 3D to the dense 2D. Yeah, so I think it's kind of similar. Yeah, basically bringing the information to the unified feature grids. Yeah, so it's more geometry consistent. Cool. And here are the losses about their paper. So they have cameras, they are using camera and LiDARs. And for the LiDARs, they are using the urban radiance field loss. So basically just a losses for the volume render depth. This is volume render depth, and this is the ground truth depth. This is one loss. And they also having this two loss. This is the occupancy loss. Basically for the points that are far away from LiDAR, they have a threshold Z. They will minimize their occupancy. So there will be no floating point before it hits the LiDAR, before it hits the surface. And they also have a loss here. Yeah, this is kind of similar. It can be, they have a Gaussian kernel or some kind of stuff, but you can imagine that is similar to finance because there are some LiDAR noise. There are some noise for the LiDAR, so you are not sure exactly where the expected surface. So they have this, they are doing a Gaussian noise and then calculating the weights and the expected weights if it's applied to the Gaussian noise. If the distribution about the LiDAR noise is similar to the Gaussian noise, you will have this loss. So this loss is kind of similar to this, but this model the noise. Yeah, so these two loss terms are used in the urban radiance field. And for the pixel camera rays, they have several loss. First, straightforward, they have the RGB loss and the sky loss. For the sky loss, in their paper, they are using a ground truth mask to basically know the separation between the sky and the foreground. This is the binary cross entropy. And for the shadow loss, similar to the D2 nerf, is trying to minimize the shadows, not explain anything to the shadows, only necessary. So it's minimizing this row, yeah, for each ray. So for each ray, you only explain is to be it's within a shadow if it's necessary. Yeah, and I think this loss, yeah, this loss is similar as before. So you are not trying to extend anything with the dynamic, so you are trying to minimize the dynamic fields. Yeah, and also one unique loss in this paper is this cycle loss. It's basically we have the flow fields. There are some cycle consistency we can apply. So basically, given the forward flow, given the x and given the t, we know the next step, and we can doing it with the next step and doing the backward flows and wait a second. Yeah, so this is the current time step. This is the next time step and doing the using the flow backward flow and getting the current one. Yeah. Backwards. Yeah.
If we one step forward and then release the backward to go back to the first.
Yeah, but why is the sum?
It's like the backward was some always, like you had some in the previous slides too.
Sorry, can you?
Velocity of backward is added to the position of this time to get 0 probably.
This is the sorry. This is the velocities for the current time step, and this is the next time steps.
This is the next position.
The next positions and getting the backward.
Backward will give you the.
Oh,
Yeah,
they should be
it-
0.
yeah,
Yeah, they
it
should
should
be.
be 0.
Oh, yeah, that makes sense. Cool. Thank you. Yeah, so basically there are some self-consistencies they try to apply before the current time step and the future time step and the past time step and the current time step. Yeah, so they are having this consistent regularization. Yeah, that's all the laws they are using. Cool. So yeah, I think I think I took a lot of time. Yeah, so for in terms of data set, they have they modify the previously Wilmer open dataset and select 120 unique sequence, 32 static, 32 dynamic, and 56 interesting snippets. And they are doing the evaluations on those and comparing the approaches on those snippets. So first of all, if you only using the 40 dynamic neural instant GP, you can see it's already a good PSNR. If we're using the instant hash table, this already surpassed the previous work by a large margin. For example, the straight surf and also the D2 nerf. But adding the flow and also the temporal aggregation about the features can further improve the performance slightly, but it's primarily improve the dynamic actors, the performance on dynamic, and also, yeah, if with everything you can see the best performance, and also the sync flow estimation accuracy is around 90%. Yeah, if without the features, it's hard to learn the sync flow, and also if phrase the features before aggregations. Yeah, I don't think this will work because there are no gradient. Yeah, I'm not exactly follow this rule. Yeah, but basically adding everything, getting the best performance.
What's the difference between scene reconstruction and no view synthesis?
Oh yeah, this one is on their static thing. This is on the dynamic thing. I think so. Yeah.
But it's also dynamic only on the scene.
This is only reported on the dynamic regions. Oh, yeah. So this is the full image. Yeah. So this is on the dynamic part. Yeah, in their data set, they know the segmentation, they know the mask for each actors, and yeah, they have the label. It's just they are not using that during the training. Cool. Okay. And yeah, I see. Yeah. Sorry, I think this scene reconstruction is the replay. This is no view synthesis is extrapolation. It's yeah.
Validation set.
Yeah, validation set. Yeah, this is the training set. Cool, and you can see it's outperform previous work by a large margin in terms of PSRs, and especially for the dynamic only, it's better. It's having better decomposition between the static thing and dynamic things. And yeah, even on the static thing is better compared to previous work, primarily due to the hash table and some advantages introduced in recent work. Yeah, and also they compare with the previously thin flow estimation approach, and the accuracy is pretty high, is around 90%. And then they propose, they're doing some downstream evaluations. So if without removing the potential encodings, then you can see the semantic occupancy prediction task, the accuracy is quite low. But if we remove the potential encoding features and then using the MLP to do that, and there are some significant improvements. Yeah, and cool. Yeah, that's basically, this demonstrates that removing the potential encoding is helpful. Yeah, cool. So the takeaway for this paper is extending the D2 nerve to the large dynamic driving scenes, and is using hash tables, LiDAR supervisions, and it's proposed to learn a flow estimation headers jointly for better consistencies. And also it's lifting the 2D vision model feature to 4D. And this paradigm can be used to transfer many things and labels, features, semantic, bounding box stuff. So the limitations mentioned in their paper is they don't handle the rolling shutter, motion blur for the camera and LiDAR, and also they do not show the geometry explicitly, and the geometry is not that good, although the rendering is okay. And also it's hard to estimating the motion about the slow moving object when actively moving very fast. Yeah, cool. Yeah, thanks everyone.
Thank you. Wait, okay. Okay, so let's move on to the next one fast. The next one is something we've covered a few times now, so it's gonna be fast. So this model was released last week, LRM, large reconstruction model for single image to 3D. Yeah, so the objective is to have one single input image, single view image, and then lift it to 3D. And these are some of the results. And the images are unposed. You don't have camera information for them, and the output is a nerve that is here transformed to a mesh. Okay, so they want to do this without any language or 2D image priors, so they don't use stable diffusion or GPT or anything. They directly want to train on 3D data that they get from Observerse and MV ImageNet, which is a large. The first one you know about. The second one is a large data set of videos of one object with the mask, the foreground mask, and the camera parameters available. And the architecture is a very large architecture of a transformer, and I'm gonna go through all of it. They start from this single image of 512 by 512, and they get the features through a convolutional layer, and then they have 3 different parts to their model. The first is an image encoder based on Dino visual transformer, and then they have this bunch of attention layers here that they call a decoder that goes from the encoded features to a triplane representation. And then after they get this triplane representation, they can use it as a nerve with a fixed MLP for all objects and get the nerve, which is then rendered or turned to a mesh for use. And this whole thing, one forward pass takes 5 seconds with the meshing, which is quite impressive. Okay, so this part is a dyno feature, like a dyno encoder that uses self-attention and some MLP layers to get all the available information about texture and geometry from this image. Then they have this learnable feature in the second part that tries to use that they use cross attention on this feature, learnable feature and the extracted features to find the important parts of the features. And then they have a bunch of self attention layers. These self attention layers are supposed to find structural pattern between the features of this learned feature to find 3D correspondence. So later when this feature is unrolled into a triplane, some points should have high correspondence to each other because they capture one part of the geometry. And okay, so this was what the cross attention and self attention layers were doing. They also take in camera parameters at training time. These camera parameters are, I'll get to it in a bit, but they're encoded and then modulated through these layers as a form of layer normalization to also incorporate the camera information in the training time. In training time, they have they take they render a few views for each object. They say they use 4 for observers, and I think the same for MV ImageNet. And they have different camera features there because of the 4 views, but in the test time, they just set it to some default value because it's just one image. And yes, so after they get this triplane, the rest is just a simple nerf. This MLP is fixed between all of the images, all of the objects. And then we have volumetric rendering. Okay. So yeah, so for their camera model, they use they model the camera using the 4x4 extrinsic model and the 4 parameters of focal length and principal points. They don't use the I don't know, the Euler angles or quaternions. They just put in the 4x4 extrinsic. So this whole thing is a 20 a vector with 20 elements. And they use 4 views per object. And the way they incorporate the camera data is using this adaptive layer norm, which takes the camera vector, puts into MLP, gets 2 scalar values, and then uses these scalar values as scale and shift in the normalization layer. As I said, they use cross attention to get the hidden geometric and textural data from the image, and then self attention to find out the 3D correspondence and structure in the feature that they learn, so they can then unravel it to a triplane. The loss they use is a pretty simple one. It's just the reconstruction loss, the photometric loss, and a semantic loss of ellipses. And okay, so I'll go to the results, but before that, the failure cases are interesting. So they show they have a blurring or not very good geometry in some cases, and they say this happens because the problem of one like single view image to 3D is ambiguous, and sometimes their model just converges to the mean model, which is interesting because Dream Fusion also says the same thing. And this model was supposed to not have this failure modes of like using 2D priors, but it does have that converging to the mean point again. And something else that they say might be the problem is that they use the default camera parameter in the test time, which is not important because of the extrinsic can be anything, but the intrinsics can be very different from what was used, like the local focal length and the principal points can be very off, so this might happen. And these are some of the results they had in the supplementary. So you can see the PSNR is actually pretty good, I guess, compared to some of the other single image to 3D models that we've seen. But like this is 0, 1, 2, 3, I guess. Yeah, I think their numbers are good, but they said that they got these results with a pretty smaller version of their model because it was too expensive to run the whole thing for getting the numbers. And going to the website to see some of their results. The results are, and the resolution is 128 by 128 from what I saw, which is pretty small and low, but there is some consistency. They don't have the Janus problem. Yeah.
They train on new data, or is it only?
Yeah, so they said Observerse is synthetic, but the ImageNet thing, the MV ImageNet thing is real data. And also they tested it on a bunch of other like Google Scan and ShapeNet and other stuff too. So some of it is real, some of it is synthetic.
But they train everyone separately or together?
Together. So the training data was like MV image, these two observers and these two together. This one has real objects and this one has rendered synthetic ones. But the test set was also like synthetic and real.
This looks so similar to the instant 3D, right?
Yeah.
Is it the same author? Or?
No, this is from Adobe.
Yeah, I should find the sample.
It is?
4 papers, just using the same power.
It's the same one?
It's the same.
Yes.
Because it's the architect is also
Architecture
exactly
is
the same.
Yeah.
The same training strategies.
And they submitted to the same conference.
Yeah, the 4 papers there.
4 papers?
Yeah.
All the two authors?
Yeah, I guess they're from the same group.
Okay.
It's from
Okay.
Yeah. What's the issue?
How do you do
One and four.
Oh, it was really.
Let's
Okay.
Remember those three?
Oh, yeah, different application.
That's odd because it's Adobe. Okay.
Yes. Yes.
Yeah.
So it won't also be released because it's on a company.
I think they said it was implemented on Tree Studio and it will be released. I think the code, not the feature.
But it's not useful.
Yeah, yeah. They used 128 GPUs for 3 days. Yeah, so it was a pretty straightforward way of doing this. The most interesting thing about this paper was the failure case, in my opinion, because I didn't expect when you train like directly on 3D data to get something like this. And this is pretty close to like I guess what is in the training data too. So yeah, that was it.
It's crazy that they use the same method figure for 2 papers. Like they didn't even bother changing the method
I
figure.
mean, how can you pitch the transformer? Like
No, but like the blocks are exact, everything is the same. Like this, they didn't even make it a different style.
let me stop recording before we. Okay.